So Zhongyi, this is Joel. We are team local quantum, and I will be presenting our result of quantum algorithm for proof optimization. So I mean, we are solving this string quadratic binary optimization problem. It's everywhere, so lots of applications and also scales exponentially. So it's a hard problem. So that's why we want to try it on quantum. First, convert it to the unconstrained optimization problem by adding penalty terms. And we use the sample-based C-var loss function to optimize our AOA circuit. I think our main novelty here is that we propose this new implemented this GPT-QAOA algorithm where we train a generative model to generate optimal QAOA circuits and the parameters. This is how the algorithm architecture looks. First, generate the operator pool with lots of QAOA type of gates with random parameters, mixer layers and cost layers. And then we generate random QAOA circuits based on the gates in the gate pool. Then we use this simulator to get the result, the distribution of each QAOA circuit. And we use this as the training data to train a GPT model. And we use the C-var loss function to update the GPT parameters, and we save the best GPT model. The best, we again sample step where we generate a few QAOA circuits from the best GPT model, and then again run it the simulator and the hardware if possible. And then we measure the bit string and do some local post-processing, local search. We believe that there are a few advantages to our algorithm. First, that it's easy to train because we only need to run quantum circuits in the pre-processing step and the sampling step. The training, city training, is completely classical. So in this way, I think we can avoid the Baron-Plato problem because the parameters are all in the classical generative model. Also, I think this is noise insensitive because we basically are training the GPT to make use of noise, for example, to escape local minimum. In this way, noise is not harmful as in normal quantum algorithm, but it becomes a useful resource. Last but not least, we believe this is the native generative model because quantum itself, it's probabilistic. And if you look at the algorithm architecture, it's the GPT is the classical generative model. The QAOA part can be seen as the quantum generative part. So it's a hybrid generative model. In this way, we can use quantum computers' exponential expressibility. So here's our result. We tried this algorithm on the 20 variable case, and we use the cumulative distribution function as the matrix. So on the x-axis, we have it's the sorted bit string. So here it's the global minimum, which is where we want to be. And here is the global maximum. And we do, so the blue lines are just the raw data. And this orange line is after a local distance one search. Roughly speaking, we have 90% chance of sampling below 10th percentile here. So I would say it's a quite nice result. I also have the live show here. So do you see my codes, right? Nice. So I mean,
Yes.
I'm gonna skip the training part, and here we directly load the best. So it's already the GPT is already trained the model now and do the sampling step. So in this step, we use the best GPT model to generate 8 QA circuits and then do the measurements or simulate the measurements to get statistics. So it's taking like 10-second computer using CPU. So this is the raw data without any post-processing. This is the left one is the probability density function.
Yeah.
So and this is the accumulated one. Okay, we then run local the post processing local distance one search, and the orange one is the after post processing. So you can see that probability is concentrating to the minimum and have the cumulative one. And we can also plot the QAOA circuits just to give you a feeling of So this is like the one generated QAOA circuit from the GPT model. I think that concludes my presentation.
Very good presentation.
Thanks.
Dr. Bimal, you have any questions?
Yeah, well, I had a couple of questions,
Sure.
right? So first, quite unique, right? So thanks for sharing this using GPT and QAO together.
Yeah,
So
thank you.
first thing is I wanted to understand, right? When you are using GPT, right? What is the token, right? Definition of token for you, right? When you are sending the token to GPT models, right? Like circuit, right? If it is a circuit within circuit, what are you exactly considering a token, right? Because see,
Yeah,
GPT models are trained for understanding language. So how do you
yeah,
take a gate type, a qubit index, right? All those things and convert it
yeah,
into
yeah.
token.
Yeah, so I think we basically treat the quantum gates as our tokens. So the index. Yeah, the index. I mean, it depend. I think it depends whether we want to use this adaptive circuit type or let's say for QLA we have fixed circuit structure, mixed layer cost. So there we actually only need to know the index or the rotation angle. So it's just a number, the index. Or yeah, when we want to have the more flexible circuit structure, we don't want to if we also want to include other type of gates there, not just a mixer like cost layer, then yeah, but I mean it's still the index of the corresponding circuit or corresponding gate. But basically we break it into very small pieces of small unitary operations. Yeah, so that's our token. Yeah,
Okay. So that
yeah.
makes sense, right? But I see you used it for 21 bonds, right? Let's say if I change that to the minimum set that we use, 31 bonds, right? Do you think
Mhm.
the GPT technology will still perform and like it will still show this robustness, right? Like and you'll still get similar returns? Do you think it will this solution, right, that you're trying to present, it's not
Yeah.
scalable given the current limitations that we have with hardware?
Well,
I think it's scalable.
yeah,
GPT does not see the band. GPT see the quantum circuit. And for example, if our quantum circuit is a 4-layer or 8-layer, for GPT it's just a 8 index or 4 index. That's quite. It's not a big problem for GPT.
yeah, we believe this is actually more scalable. Basically, we take part of this whole circuit as one token. And if the circuit becomes bigger, we can just choose a bigger, like the bigger tokens there. So I think like this scales better than the normal VQC, VQE approach. That's our feeling, yeah.
Okay. Makes sense. I noticed you had one NumPy file, right? The operator pool for best model. So what were the pools? Sorry, what were the gates that you used in that pool, right? Like were the single qubit gates, right? Or what kind of gates did you use
Yeah,
and why,
I mean,
right?
we
What was the reason
basically
for that?
yeah, we basically just use normal QA gates. Like you have the mixer Hamiltonian, and then you
Hmm.
rotate it with some random parameters. And in this case, that's the rotation angle is all like or different parameters gives different gates or different
So what kind
significance.
of mixture did you use? The standard mixture or like was it a constraint aware mixture? Like what kind of mixture was it?
What kind of, sorry, what?
The mixture, you mentioned you use a mixture, right, for the Hamiltonian. So what kind of was it? Like there are different kinds of mixture you can use, right? So is it
Yeah,
the
yeah,
standard
Hamilton.
mixture that you've used?
You mean the Hamiltonian, like cost
Yeah.
and for the cost Hamiltonian, we use the objective function, like basically the same as the case in provided by the Vanguard example. So
Mhm.
yeah, so but for the mixed layer, it's just mixing all the qubits. It's like yeah, it's like all the x, a single qubit x added together like that. Yeah.
And did you measure the depth parameter when you ran this? I think you ran it for 10 epochs, right? Like, was there any penalties that you observed, right? What was the depth parameter with every run that you did?
What's the parameter? Sorry.
The depth, the depth of the
Yeah,
circuit, like
depth.
how deep did it go? Yeah.
So we use four layers of QAOE circuits. Each layer is basically it's a one cost layer, and one mixer layer, and one cost layer, one mixer layer. I believe that the mixer layer is just a single layer, just a
Hmm.
bunch of X rotations. But for the cost layer, you have the all those, let's say here RZ, those gates. So I think for one, if I understand it correctly, like probably this is one layer. So one cost layer is 1, 2, 3, 4, 5, 6, 7, 7 to 4. Yeah, like you need to run 7 to 4 gates sequentially for one layer. So I think that would give maybe a 40 or a 30. The depth will be 30, 40, something like that, I think. Like on the
Okay.
physical level, yeah.
And did you compare your results to the classical optimizer? I saw that somewhere, right? Like, but I was
Yeah,
not
yeah,
sure which classical.
yeah, we compared, but I think the thing is we compared it to the continuous solver. We didn't run the classical solver for a combinatory case. We just used the continuous optimizer. And
Why?
well, yeah, that's a very good question. I guess we didn't really find, we just took the optimizer from Python. I think those were the easy ones to implement. I mean, we would love to compare to like more like the classical solver that's specifically for combinatory problems, but we didn't find one. Yeah, yeah,
All right.
yeah.
Okay, no, great. Thank you. Those were my main questions, right? So thanks for taking time and presenting this. Really interesting premise. Thanks, Team Loco.
Thank you. Stop sharing that.
Thank you, Team Loco. It was very great. So
Thanks.
next, we'll go to team number 2. It's MOH_group and Mohammed.
We can share the screen now.
Are you ready? Yes, you can share the screen. Yes.
Yeah. Does it appear now?
Yeah, you can start with the presentation.
Okay. Hello, everyone. The first question that we asked about this challenge is, what is the problem with the classical optimizers? Like we have a Groovy, we have Cplex from IBM. What is the problem? The problem is time consuming to find best solution. We need to speed up with quantum algorithms like a quantum optimizer, QAOA or a VQE. But there's a problem with the QAOA and VQE. The problem is how to initialize algorithms to get the better result. So we ask ourselves another question: why we can't merge them together, get the advantages from classical solvers like Groovy and quantum solvers like QAOA or VQE? So we build our approach. Quantum enhanced portfolio optimization. We are bridging classical and the quantum computing. Our approach is a hybrid approach. For scalability, we solve the problem of time consuming from classical, solve the problem for QAOA and VQE that suffer initialization in the beginning of algorithms. So the innovation is classical warm start. We run the solvers, classical solvers, before quantum algorithms. So we have a good initial results and feed those results to quantum algorithms to get more speed up. We use a financial data that has been provided through GitHub repository. We use a hybrid approach using Groovy, but we can, in this approach, we can use any classical solver to speed up. We run Groovy few time, like 1 minute or 2 minutes, and then applied VQE and the QAOA optimization. We run our solution, our demo solution on IBM hardware quantum computers. So we the known pipeline is to get the classical data converted to Cubo and Ising model, and then to Pauli operator, and then feed it to algorithms. We are using API authentication, and we used hardware and simulated running in the back end. Our results, we get a result to compare what is the advantage of the warm start. So we get without warm QAOA and VQE, without warm start, 4 seconds, and here 3 seconds. In the algorithms with warm start, we get in much fewer time in QAOA and also fewer time in VQE. So those our result, and this is a plots for comparing. We are seeing now much speed up using warm start, and we have a good accuracy the QAOA. Our conclusion: we have now a new algorithm or a new methodology that we can use to achieve a good result in NISC computers that we have now.
Wrap it up. Go on.
Our vision to new things to this methodology that can be part of a huge system that might be tomorrow's Aladdin alternative system. Thank you for listening. My name is Muhammad Hanani, and we are MOH Group, Wais, Ishtiyaq, and Wa'amil Ali.
Great presentation. We'll go for questions. Dr. Bimal, you have any questions?
Yeah, so I'm a little bit, thanks for the presentation, right? But I was looking at your README, right? So in the README, you have basically defined, right, the objective function, correct? And when I basically look at your code, right, I don't see upper bounds, right? Like, are you, and then basically, how are you using that? Like, can you share that, right, within the code? Like, I was like trying to map your objective function that you have in the README to the code, right? But I was not able to see the exact formula and I was looking at Cubo Converter, right? You have a file called Cubo Converter, and I was looking at that.
Yeah.
So I was not able to replicate it.
Yeah, we use our converters. Depends on papers that we mentioned here, and they have used this methodology and they get good result from it. The focus on final run because it's the summary of what we did work. This is a demonstration prototype of our methodology. We haven't that much of time to improve it, but we know our misses. We have kind of a lot of misses, but we know how to fix it.
Okay, so then what was the exact objective function, right, that you used in your converter, in the Cubo converter? If you can update that, right, so that we can validate like where it is going, right, and exactly how it is tying back to the solution, because I'm not able to reproduce, right, exactly what happened here. So that is the challenge I'm having.
Are you facing a challenge with understanding how can we avert the problem?
Yes, correct. How did you convert? So the cuboconverter.py file, it is actually not in sync with your README, right? So that is the challenge I'm having. Like your README and cuboconverter both are out of sync. Yeah.
Our solution with the notebook is showing how pipeline is works. So if you have read the pipeline, you can see we get the data from the Excel data that has
No,
been
that I got it,
provided.
right? I'm able to
Yeah.
run that part, right? What I'm trying to see is the problem, right? Like the index tracking that we are trying to solve over here and what constraints we are using and how we are using. So for that, when I was looking at your README, right, you have a function defined. But when I try to run that function, right, in
Yeah.
Cubo Converter, it's not giving the exact same results, right? So I was like a bit confused. What is the function you are using, right, throughout the notebook? It's not stated explicitly anywhere.
This is a demonstration, so we just want to arrive the idea. we can work well on our project, but we have some time limitations, so we didn't focus on everything in converting.
Okay, all right. One more question I had was, yeah, go ahead.
I will answer to that question. My name is Wes. Hi.
Okay.
So the thing
Hi.
is that question, you are right about some mishaps, but the thing is we are working currently, as you see, we have proposed a hybrid classical approach. So by the converters that we have proposed, there were some errors in it, but we know the solution about it, and we are working on, if we in the future we will work on the how to fix this problem. And with this problem, if we are working on this fix, will allow us to better optimize our better control. The thing is that with the variables there might be some mishaps with the variables, but the thing is we do apply the analogy of the Vanguard variable and the integration with the QAOA. So the thing is this is just, consider this as just as a test case of the Vanguard hybrid classical optimization approach. And we are, since it is still in the stages of improvement, so we are still considering that it will give us more better optimization.
Okay, that makes sense. And I had another question, like I saw you guys run it on the IBM hardware, right? And I saw you used around 6 to 8 qubits. So what did you do, right, in that? Like, that was also not clear. Did you reduce the 31 bond problem to 6 to 8 qubits? If you did that, like how exactly did you reduce that? And
Yeah,
then
we have
like, yeah, go ahead.
we have a limitation in our account, IBM. So we reduced the 50 to 15. We use some related data. We use paper-based parameters that us to make this reduction.
Okay, got it. And then and basically I saw like in one of files, right, you were saying like 100% constraint compliance. Like, what does that mean? Like 100% constraint compliance?
Yeah, that's like achieve all constraints that assets or data are facing.
And how do you do that? Because that's like a very big claim, right? So how do you do that?
Let me just.
Because validating that, right, once you solve it is a challenge. So if you claim that, right, it's 100% compliant, like how do you validate that? And where do you validate that?
So the validation, it's come with converting the problem. So you decide the constraints of this asset or this data. You feed it in B file.
Mm-hmm.
So it's in the linear programming in linear problem file.
Okay, I get it. So you are basically still referring to the one that we had set in as the linear constraints. Okay.
Yeah.
Okay, makes sense. All right. Yeah, those were my main questions. Thanks, team. Good work.
Thanks.
Thank you for the questions.
Thanks all for listening. Thank you for your question.
Okay, overall
Sure.
great presentation, great work. Yeah, we will move to team number 3 with support for Q. You can. Okay, hey Veronica.
Hello, everyone.
Yes, you can start your.
You can hear me, right?
Yes, we can hear you.
Sweet. Okay, perfect. So we are Team Portfolio. My name is Tibor. Welcome. Classically, solving large constraint quadratic problems, especially with binary or integer variables, is NP hard and scales poorly. Portfolio optimization is a prime example. It quickly becomes intractable for traditional solvers as constraints and size grows. These problems show up in finance, resource allocation, and logistics, where better solutions have major real-world impact. Efficient hybrid algorithms, like the VQE, could help tackle them faster or more effectively on near-term quantum hardware. And in this work, we explore quantum optimization for constraint portfolio optimization, formulated as a binary quadratic problem with linear constraints, or QUBO with penalties. So rather than starting from scratch, we aim to build upon this foundation we received. to conduct further research. We set out to improve the performance of VQE on a constrained portfolio optimization problem, formulated as a QBO with penalty terms. Our approach started from the provided GitHub repo, where we reproduced the 31 bond result and analyzed performance. We then varied parameters to find the most robust configuration and extended the study to synthetic problems of different sizes, which allowed us to perform both scaling analysis and statistical testing. Our project had 4 main goals. First, to explore the best ansatz and better parameter settings for fast, high-quality conversions. Second, to benchmark the impact of penalty values and initialization strategies. Third, to extend the study by testing scalability and statistical robustness. And finally, as a novelty, to investigate new ansatz design. So the structure is explore, benchmark, extend, novelty. From the provided GitHub evaluations, we chose the best settings for the 2 local and BFCD ansatzes. These gave us the best balance of conversion speed and optimality, and we used them as our baseline for further benchmarking. For benchmarking, we focused on 2 factors, the penalty value and initialization. We tested penalty values from 1.1 to 2.5 and found 1.1 gave the best convergence with constraint satisfaction of 80% for 2 local and 90% for BFCD. For initialization, we tested pi over 3 versus random. Pi over 3 gave highest constraint satisfaction, 80% for 2 local, and 70% for BFCD, while random starts showed mixed performance. Next, we extended. So we built a problem generator to create synthetic data for a given number of bonds and used it to test scalability and statistics. First, we tested scalability using random problems with sizes 15, 20, 25, and 30 bonds, running 10 attempts each. As expected, runtime grew with size, but more importantly, the gap between the optimal solution increased. This likely comes from the interplay between growing number of qubits and their 4 parameters and the ansatz topology. Next, to statistics. We ran detailed statistics on 30 bond problems. We compared 100 runs of the same problem with single run of 100 different problems. For different problems, about half were solved optimally in one shot, but around 5% had gaps, over 50% showing a long tail of hard cases. For repeated runs of a mildly difficult problem, we see that about 20% worse than optimum is the average solution, with high variance and optimal solutions found in less than 5% of the runs. As a novelty, we implemented the heat exchange ansatz. It doubles the qubit number by adding buff qubits, but remains shallow using only XX and YY gates, which makes it hardware friendly. Since the ansatz is the heart of VQE, and our tests with 2 local and BFCD showed limited performance, we explored this new design as a promising direction. To conclude, our next steps are to integrate this heat exchange ansatz fully into the VQE pipeline and develop better feasibility matrix to balance speed and accuracy. We also plan to extend scaling tests to real quantum hardware and explore new ansatzes and solvers to handle hard cases and reduce variance. Yeah, thank you very much for your attention.
Thank you. Thank you for your presentation. Passed on to Dr. Bimal for any questions.
Yes. Yeah, thanks for the presentation, right? I see basically you converted this problem into a QBO problem, right? Like you are basically using the binary optimization method for this one. So where exactly are you converting that objective function, right? That particular QBO, right? Which is your Hamiltonian. Like where exactly is that construction happening? Can you show that?
So this is based entirely on the GitHub repo. So this happens in the same place in the original GitHub repo. This is just reusing these API calls.
Okay, so you are using the original constraint problem that was defined by our team, right? And utilizing that. Is that correct?
That's partly correct. We tested this problem, but our statistics actually is a random problem generator, which we also include and package there. All of these random problems are getting converted to using your team's converter to Qubole, but we spend an awful lot of time to try to reproduce difficult financial problems given limited access to the data.
Okay, makes sense. Then basically you were swapping penalties, right? I saw a lot of times, like I saw values 1.1, 1.5 and all that. How did you come up with those, right? Like how did you decide, right, which is the best feasibility rate, right, and the best feasibility objective based on a given penalty, right, for each of that particular circuit or the ansatz, right? Like what was the process that you followed for that and how did you come up with that?
Nick, and I think that I can answer to this question. It was that we built everything using provided GitHub repository, and we added there because there was default value of the penalty. So we changed this code to ability to change this value, and then we test for the given penalty values which we showed. And after obtaining all the results, we analyzed and checked if any constraint was satisfied. And it was the way how we analyzed this.
Okay. Right. Then I had one interesting question on that heat exchange ansatz, right, that you referred in the presentation as well as in the submission that you did, right? Can you explain a little bit more about that, right? Like what exact Hamiltonian terms, right, it uses, right, and how is it different, right, from the other ansatz, right, like that are being used, and like what was the circuit that you created for that, right, and like that circuit, right, how well did it perform, and did you measure depth of that circuit, right? What did it take too long? Was it costly? Did you spend more time on that, or is it just like you experimented with it?
Can you go one slide back or two slides back, Chichibe? Okay, so here is this ansatz. So we didn't have enough time to integrate this ansatz with our QE workflow, which with the provided GitHub, but we already implemented just in Qiskit without running whole experiment. So this ansatz uses like double number of qubits because the idea is that we add a given number of bonds, we double the number of actually qubits which we use. So using this ansatz based on double the number of qubits we use, but the way in which these qubits can talk to each other is very limited. So we have just XX blocks and YY blocks where one qubit, let's say from the problem side, talk just with one qubit with the buff qubits. So this, I think this helped to be a little bit lighter for the hardware, but we didn't have enough time to express more.
Okay, got it. Okay, and you basically use the term called bilinear entanglement, right? Somewhere in your repo that when I was going through it. What exactly does that mean? What do you do? Like I'm not much familiar with that bilinear entanglement that you applied.
Actually, this to choose these ansatzes with these parameters, so with the topology which is bilinear, we base on the results which were provided. So there was two cases explored. One was the bilinear connection between qubits. Just two qubits can talk to each other, but for two local, there was another way. So each qubit can talk to each other qubit. And from these two scenarios, which was the bilinear, so the way where just pair of qubits can talk to each other.
Okay. All right. And just one last question, right? So the penalty terms, right, that you came up with initially, right, and the ansatz that you selected, how does this scale, right? Like if let's say you tested it for 15 qubits, 20 qubits, 30 qubits, 50 qubits, in your opinion, I know you have not tested that, right? But how will this scale, right, as you increase the number of bonds? And let's say with the bonds, you also increase the bond indexes, correct? How will this scale?
So maybe I'll take this one, or Veronica, do you want to go?
Yeah, sure. Go ahead.
Okay, so in general, our testing is pretty pessimistic when it comes to this approach. So in general, I believe not even the time, but just discrepancy, as you see here, keeps rising. So how far you get from the solution keeps rising with the amount of bonds, which is pretty scary. The more you have, the worse it gets. So this really points you to the fact that you need to do some groundwork because this is just not scaling. That's why this somehow gave us the hint that maybe start with a new ansatz from the get-go.
Right, exactly. Okay, yeah, that answers my question. Thanks. Thank you, team.
Thank you.
Thank you very much.
Thank you.
Thank you for presenting. Great questions, great answers. Okay, can you stop sharing the screen? We'll move to the next team. Okay, the next team from Q Frontier, it's Hein, Zhe, or Ho. Are you ready?
Hi, yes. Just
Yeah.
give me one second. Let me
Continue.
share my screen right here. All right.
Yes.
Can everyone see the screen here?
Yes, we can see. Go
All
on.
right. Well, hello everyone. My name is Hein, and together with Mac here, we are excited to present our project. For task 1, we replicated the mathematical formulation and performed constrained random search. The heat map on the right shows a sector by characteristic exposure of the selected portfolio. In task 2, we converted the problem into a binary decision variable, so it's a 1 if the bond is selected and 0 if it is not. For task 3, we ran QAOA and VQE on a quantum simulator to generate bond selections. Tasks 4 and 5 will be explained in detail later on. In task 4 here, we used quantum routines to solve the mathematical formulation for task 1. Our models were subjected to numerous constraints, but the following are some of the most important ones. The key idea of the objective function here is to minimize the deviation from sector targets based on the portfolio market value, or PMV, and duration times spread, or DXS. For the second constraint here, the main rule is to ensure total portfolio value stays within cache limits, keeping market value between set bounds, of course. The third constraint enforces sector risk limits by keeping each PMV and duration time spread within predefined bounds. Finally, the last constraint controls portfolio diversification by capping how many bonds can be selected per sector, which prevents concentration in one sector. Here, the QAOA has a diminishing loss curve, and on the right, see the bond selection results. The VQE results for 140 iterations, and similarly, bond selection results are on the right. This simulation here visualizes the VQE at work. The y-axis represents the energy of our system, but in financial terms, think of this more like a cost or penalty of a potential investment portfolio. The algorithm's job is to find the portfolio with the lowest cost, which you can see in action here, driving the energy value downwards. Each point on this line represents the evaluation of a different random portfolio combination. The rapid drop at the beginning shows that the algorithm is learning quickly, and the flattening curve at the end shows it's converging on the very best solution. A classical computer would take much longer to find a high-quality solution, while our quantum algorithm navigates this efficiently. And the outcome is shown on the right, tells us which bonds to select and which bonds to neglect, and not just some cost value. And of course, this selection satisfies all constraints and objectives. And this is the VQE for iteration. To increase the number of iterations, the bond selection also increases. For task 5, to compare results, we ran each QA quantum selection through the benchmark model, checking every hard constraint and logging any violations. If a selection failed, we applied repair heuristics and retested it. Only feasible portfolios were then compared on objective value. These steps ensure that when comparing performances among different quantum and classical approaches, we are comparing apples to apples and not to oranges, for example. So both QAOA and VQE produce simulations with solutions within a few thousandths of a percent of the classical optimum, even for a different number of bonds. All feasible quantum solutions match the benchmark's hard constraint, showing that quantum optimization can meet strict portfolio requirements. In conclusion, the solution matched the classical objective value on our bond selection task, We validated feasibility by running quantum picks through the classical constraint checker. In terms of scalability, results held across different problem sizes. We applied the same constraint to quantum and classical approaches, ensuring the performance comparison is an apples-to-apples comparison. Since from our work, we have demonstrated that quantum already matches classical quality. We only stand to gain as the hardware improves. Our future scope is to scale up by using better hardware to handle larger portfolios with 19 plus bonds, and refine the math formulation by reintroducing allocations and auxiliary variables. We'll also explore various noise mitigation techniques and test alternative circuit designs such as QAO, adaptive QAOA, or hardware efficient ansatz. We also plan to explore hybrid quantum classical methods and ultimately integrate quantum routines directly into the full optimization pipeline for faster decision making. Well, thank you very much for your time and attention. And if any of you have any questions, Mag and I will try our best to answer them. Thank you very much.
Great presentation. Okay. Dr. Bimal, you have any questions?
Yeah, thanks for the presentation. I have a couple of questions, right? Looking at your repo, right? So first thing is like what I didn't understand is you use docplex, correct? Is that right? And from the docplex, right, to the cost function, right, within Cubo, where is that mapping being done? Like, how are you doing that, right? Like, I was a bit confused. I didn't find that. And then when I was looking at there was a file, right, a JSON file, right, which was the bond data JSON file. And I saw many bonds had like unclear units, right? Like we had some certain ranges, right? 0.02234, and like we saw values like 0.03, right? And then the bounds were not correctly mapped, right? Like, so what exactly is that file doing, right? Bond data JSON, if you can explain that, right? And how are you using that? So those were the two questions I had.
Sure, yeah. I think Mac will be responsible for this section. Could you jump in and answer that? Sorry.
Yes. For example, we construct the JSON field from the duplex information and the GitHub. So I do some modification in the data. Some data is not available in the duplex field. I do some I construct some data in order to complete the number of variables we use and the quantum algorithms.
Okay, so those were like manual changes you did to the data. So those were not like docplex generated. Okay.
Yes, it's some manuals there to run the quantum algorithms.
Okay. And then I was looking at your QAOA optimization, right, notebook, but I didn't see anywhere, right, where you are setting what you call the hyperparameters, right? Like what kind of how many shots, right? What kind of noise you want to model and etc. Right? Did you try that, or is it missing, or like I didn't get that part, right?
The noise mitigation error. Okay. The parameter I use is one parameter per qubit. In this case, I use 19 qubit because we use 19 bond to try the quantum algorithms. Okay, I check.
Okay. And in your presentation, right, you basically said like you made a claim, right, which is like almost both of the solutions are what you call similar, like the classical and the quantum. You're able to get the quantum equivalent, right? Very less parity. I saw like almost 10 to the power minus 3, right, over there. Like how do you substantiate that claim, right? Like someone questions that, right? How do you make sure like okay, this is the thing that we did, right? And this is how we can reproduce this without doing any manual tweaks, right? Because a lot of manual tweaks were done. That is what I saw. Like if you don't do those manual tweaks, right? How good do you think your solution will work? Given the time constraint, I understand you did some manual tweaks, right? But without those, how will you basically prove that kind of a claim?
I think for the classical and the quantum, you use the same content, the same variable values, and to do the a fairly comparison between the classical results and the quantum results. For example, we get this achievement 10 minus 3 comparison to the classical algorithms. I think you have to use the same number of variables, the same number of content.
Correct, exactly. You need to do that, right? But what I saw is the constraints were differing, right? When looking at the file, there was some manual tweaks done to those constraints, right? So I'm saying like without that, right? If you do it without those things, do you still think you will be able to achieve the same results?
I think real values or real world application, the algorithm should behave in the same way the manual values we use, for example, is the same behaviors.
No, so I'll give you an example, right? So in the LP, right? In the LP file, right? There are like constraints that we use, right? The sector bounds, the PMV DXX bounds, we use cache limit, right? And then the per bond mix caps, right? The per bond caps. But I didn't see those same constraints, right? In the quantum bit strings when you are scoring that, right? So how can you say like it's exactly the same constraints you are using?
Can you answer this, Heinz, if you want somebody?
Oh, so you were asking about how for the quantum constraints, right, on the QAOA side?
Correct, because see, in the LP file, you'll see a lot more constraints. You'll see sector constraints, you'll see cache limit, you'll see the bond, what you call the mix caps, right? The caps that we have for the bond. But how I didn't find those constraints, right? When I looked at your quantum bit strings, right? I didn't see those, right? So when you say okay, you're using exactly the same constraints, right? That claim is not correct in my opinion, right? The constraints that you guys are using are slightly different, or maybe quite different than the ones that are there in the LP file.
Okay. In terms of QAOA, Mac was responsible. The quantum side wasn't working on that, but for more like the classical side, I drew in the constraints directly from the LP, and then I drew like the results directly from the LP and the JSON file provided by Mac, and then like I made sure that like because like different algorithms have different cost functions, I made sure that like the I made sure that the energy value are comparable to one another. So I'm not too sure about the QAOA side.
Okay. Yeah, VQI, I see that, right? I was more around the QA side. So on the VQE side, right, I had another question. Your VQE optimization looks pretty good, right? The way it's implemented, right? And did you try CVAR, right, VQ? Because like, let's say for better feasibility, did you give that a shot or you stopped over here?
I think we just stopped over here. We went with C pledge because
Okay.
I've messed with that before, so that's all. Yeah, sorry.
All right, no worries. Yeah, but this one is pretty good in terms of results. All right,
Okay.
yeah, those are my main
All right.
questions. Thank you.
Thank you
Thank
very
you
much.
very
Thank you.
much.
Thank Hein and Mac presentation.
Thank you.
Okay, next I will go to next team, superposition squared. Present Diana.
Hello, I'm sharing my screen.
Yes.
Okay, so I'll just do desktop. Okay.
Yes, we can see your screen. You can start.
Okay, so hello, we are team superposition. Sorry, I'm just gonna. And so our project was, we were given the financial data and we tried to minimize the cost of buying the bonds while also maximize the cost of selling them. And we were able to simulate a quantum algorithm and compare it to a classical one to see which one performed better. So for our approach, we use Qiskit and Python to code an implementation of VQE, which some of the other teams have done. And our pipeline was basically taking it in. And one thing that we did differently was we created a trading strategy matrix that used Cubo, but it's more like linear algebra perspective, if that makes sense, with the matrix. And then we used VQE once we had the matrix, and then that's how we were able to select how to optimize the portfolio. And so once we got the values, then we actually were able to do some data analysis on how the algorithm was doing and even the types of like the percentages and everything. So we weren't able to use IBM computers, so I just ran everything locally, which is why the classical algorithm is like faster than the quantum one. But if we did have access to quantum computers, I do think it would be better. And this is evident here when we have like a -% for the quantum advantage. But we were able to implement it though, so that's what matters. And so again, we were able to also look at like the cost of the algorithms and then the qubits, parameters, and gates. Okay, so this matters because if the financial industry is able to use better algorithms, it will help with having more efficient use of resources like funding and hardware, but most importantly, time, because quantum algorithms are meant to be faster than classical ones, which will help with better trading and eventually better profit. And so, as mentioned already, we also were able to look at the data analysis of the algorithms. And so to extend our project, we definitely like to receive access to IBM Cloud to run on quantum hardware. And then our current approach looks at the VQE algorithm. And so we also used like Cubo for it. And currently our approach only looks at the diagonal entries, and we would try to have like more parameters and penalties in the matrix to just evolve it more as an algorithm. And so now I'm going to show you guys the code. So I have a few. The first one I have is the Excel loader, which loads in the data and also cleans it based on the parameters and the characteristics and the features if we did have a model, which is another thing I think would be really cool to implement in the future. Have a quantum machine learning model that's able to help predict and optimize how to sell the bonds for profit. And so once I run this one, then able to quantum portfolio optimizer, which is where we have like the algorithms based. So we have the classical greedy algorithm. We also, Qiskit imports, analyzing the data, building the matrix, and creating the targets for it based on constraints. So we have like budget or also risk, and then enhancing the matrix. So I also have, and then this is where we have the Cubo to poly operator. And this is where I'd like to make this better with the off-diagonal terms. So I have a notebook where I go through like a smaller process, but it's basically the same thing, but just put into the notebook. So we would run it. We get we get the imports, then we load in the data. So right now it's loading it in. We have the bonds, so it loaded. Then we have the comparison analysis here. And it even tells us like the assets selected and the runtime cost. Then we have, so one thing I'd like to add in the future is also like more analysis on the financial side of like how much the bonds cost. So once we run this one, this shows the visuals. Then we also have analysis.
Wrap it up, yeah. Wrap it up.
So we have like this and I'd like to make this more financial, looking more at the financial data as well. And then this one is just interactive, so you could see those. And then we have the analysis here of the VQE. And then we have the trading strategy. And then finally, the overall, all the metrics. This part just exports all of the data that we have here into a JSON file. And so that's basically our project. Thank you so much for listening.
Great presentation.
Thank you.
Thank you.
Yeah, thanks, Diana. Diana, I had one question, right? Like I was going through your code, right? And I see basically you're trying to do the risk return, right? Like you're trying to minimize the cost and increase the yield, right? But when you are trying to do that, right? Like where is the budget being enforced, right? Like I looked at your function build a trading cubo matrix, but I didn't see any enforcement budget, like select at most this many bonds or select n out of this. The risk of that is it might select a zero matrix, right? And then basically do that. So how are you enforcing that? Like, can you explain that?
So right now, we weren't able to implement that specifically. Like, I definitely want the budget to be one of the constraints. I just wasn't able to include it with this specific one. But that's one thing I wanted to add with saying like making the matrix better. That's definitely something I care about because I think that's very important for finance. And thank you for bringing that up.
Yeah, because that's very important because there is an inherent risk, right? It can just create a zero matrix sometimes, right? And it will think it's basically found a solution, but actually it's not a solution, right? So that's like a very big risk over there. Okay. And another question I had, right? Like in your particular this thing solution, right, that you are trying to build. I see it's mostly RY and CZ gates, right? Like, but don't you think like as your N grows, right, that gate that your circuit depth will increase, right? Have you thought about a different kind of what you
That's
call?
like the guide rails or like the limits of when it should stop. I haven't thought about it like I haven't so when we were coding it first, I just wanted to get it running, but now that we have it running, that's definitely something like with machine learning model, I mean, like when I mentioned it, I think it'd be really interesting to add that because that is important and you want to have a good model that's able to stop at a certain point. And these are all really good points that I wish we would have had time to implement. And I really appreciate that you brought them up.
Sure, no worries. And then when you are preparing your quantum data set, right, I saw you are using a selection strategy diverse. What exactly is diverse? I'm not familiar with that. Like, what kind of sampling does it use?
So it was mainly, it's just trying to look at the different characteristics and it could be changed based on the columns of the data and the parameters really. So when I say diverse, it's not random, but it's based on how whoever's running the model, they can choose like which columns they want to use.
Okay. And then there was one thing that was mentioned, right, in somewhere in your presentation, the liquidity considerations, right, that you are basically stressing quite a bit. Can you tell me exactly, right, like where is that happening? Like how are you basically focusing on that, right? Because that is one of the things we also focus, but I want to see where exactly you are focusing on, right? What formula did you use for that?
For the liquidity, I do have a form for it, but I don't know it off of the top of my head right now. I know it was subtracting the amount of like the cost for buying and selling. It was like the average cost and then like dividing it. But I know it was something manually implemented.
Yeah, okay, because I didn't see it in the code, so I'll recheck if it is also manually mentioned anywhere. Okay. And one last question, right? Or VQE that you have. So what exactly is happening within that solve quantum VQE manual function, right? Like I didn't understand or grasp that, right? Like what is it calling, right? And how is that manual looping happening, right? Like what is it changing? The convergence, if it is changing the convergence, how is it changing that, right? Like can you explain that function a little bit?
Yes, so it's converting the cubo to a Hamiltonian and then it's creating anstats, like the circuits and everything with the qubits. And then it's basically just taking in the parameters, I believe. I don't know too much on more than that. I know it was just like setting the foundation for the circuits.
Okay, got it. So it's more like you were just experimenting with that, right? It's not like you were comparing that. Okay, makes sense. And
Yes.
then one more thing, right? I see you also model for noise, right? What did you use in that AER library, right, for noise resiliency?
Yes, so I used the AER simulator and then I used an estimator from the Qiskit library.
Okay, got it. All right. Yeah, good. Thank you. Thanks, Diana.
Thank you so much.
Hello. Yeah. Diana, just one question. I'm just going through your notebook. So in VQA quantum circuit complexity analysis, right? You mentioned you have 64 gates and the circuit depth is 1. So all the 64 gates acts in parallel. I mean, like the circuit depth is number of layers you have run simultaneously, right? You got circuit depth 1. You mentioned in the graphs you showed in the presentation.
I'm looking at it right now.
Yeah, in the VQ quantum circuit complexity. Yeah.
Do you happen to know which cell it is for?
63. I mean, the execution number input 63.
Oh,
Yeah, the graphs.
okay.
Quantum circuit complexity, you have like 16 qubits, 32 parameters. Circuit depth is 1, and number of gates is 64. So if the circuit depth is 1, and if you have 64 gates, all the gates should be parallel. Is that correct?
So I'm not sure why it did that.
Okay.
I'm really sorry. Thank you. I will look into that.
Sure, no worries. Yeah. Just want to make sure.
Thank you.
Okay, okay, we'll go to the next team. It's a collective qubits. Team 6. Satvik, are you ready?
Actually, Caleb was presenting.
Okay, no worries. Okay, you can start.
Computer's showing some faults.
Okay. Good day, everyone. Please, can you hear me?
Yes, we can hear you.
Okay. So we are Team Collective we are Team Collective, and we are here to present on our quantum enhanced portfolio optimization. This work combines the classical finance techniques with cutting-edge quantum algorithm. And in our work, our project focuses on creating a hybrid framework that brings together classical and quantum methods. And we compared a quantum enhanced portfolio against a classical benchmark, that is the GROBI, using matrices like the annualized returns, Sharpe ratio, and portfolio risk. Our goal was to test whether the quantum method can cover more efficient and diverse portfolios. Certain key features of our work was that approach have 5 main components: a robust factor model, via principal component analysis to stabilize the covariance estimation. And now a classical benchmark using the GROBI is used to serve as a baseline. A precise QBO problem formulation, turning finance into quantum-friendly optimization problem. Our effort was to integrate a paneling for the QAO, that is the quantum approximate optimization algorithm. A systematic hyperparameter tuning to ensure fairness and robustness in our comparison was done. Beginning with our covariance estimation, we know that asset returns are influenced partly by common factors like the market trend. And we used a principal coefficient analysis, the principal component analysis, where the formula we used was the sigma is equal to the B, that is the factor loading, which shows how much stock is influenced by hidden market factors, followed by the factor covariance, where it shows the hidden factor related to each other, in addition to the diagonal or the asset-specific risks. The result is more stable. The result is a more stable covariance matrix, which avoids the noise we get from raw historical returns. A QBO formulation. Here, we move on to our optimization, where the portfolio selection is turned into a quadratic unconstrained binary operation. This way, the X here represents the vector of decision. That is 1 if an asset is selected and 0 if asset is not selected. And the Q there encodes the risk, the returns, and the constraint. So the cost function gives us a score for each given portfolio. Our job is to minimize it, which means finding the best trade-off between risk and returns under given constraints. We implemented the quantum approximate optimization algorithm with paneling. To solve this, we implemented this algorithm. Each asset is represented by a qubit, and then the algorithm alternates between 2 steps. the cost Hamiltonian, which encodes our portfolio optimization problem. Then the mixture Hamiltonian, which explores possible portfolio combinations. There was a tuning parameters where the cost Hamiltonian is represented by gamma and the mixed Hamiltonian represented by beta. The gamma marks which portfolio is good or bad based on the cost function. And then the B stir up the states we explored over the other portfolio combinations. We implemented paneling lightning qubit simulator with 10,000 shots. And this is our workflow. Here we initialize the quantum states where all portfolio equally. Can I continue?
Yeah, 30 seconds, wrap it up. Go.
Okay. Then so this was our workflow where they initialize a quantum state, apply the problem unitary to score the portfolios. Then the mixture, which is the mixture Hamiltonian, was used to explore alternatives. We measured our quantum states to get the candidate portfolios. And we followed by a classical optimizer, which is the Adam optimizer, was used to update the gamma and the beta variable. We repeat these processes until a convergence is attained. Up to our hyperparameters tuning, such the risk aversion, which shows how much we care about minimizing the risk versus maximizing the return. Secondly, the number of the QAO layers were increased, where deeper circuits shows a better solution, but more complex. But it is more complex. We use an executive grade search to systematically test the combination. This ensures
I'm
fairness.
sorry to disturb.
And
Can you conclude it? Yeah, I'm sorry.
okay, I was mentioning the upper parameters we actually did.
Yeah, conclude
Okay.
your presentation. Yes.
All right. So this was our results, which shows return was it was close to 100%, not 100%. It was 0.999, and our matrices like the performance was also show the Sharpe ratio, which the classical or the Gubic gave us 1.65. With the quantum, the Sharpe ratio increases to 2.23. And then this results of the cost function values against the iterations, followed by these are some future enhancement that we can actually work on and improved. And at the end, this is what we had for our overall tuning. Thank you.
Great presentation. Dr. Bimal, you have any questions?
Yeah, thanks for the presentation. Few questions, right? So the first one related to your cost function, right? So you are using Cubo, right? If I'm not wrong, right? And then
Yes.
you are optimizing the Cubo energy. But then why are you picking the Sharpe ratio as your metric, right? Like I see you are sampling you're determining what is the best Sharpe ratio, right? Like, see, when you are using Cubo, right, you need to use the energy minimizer, correct? That is your best Sharpe ratio. But then you are using it among the sampled bit strings instead of using the energy itself. Like, why is that?
Sorry, please, one more, the question again. I didn't hear you.
So your Sharpe ratio, right, the one that you're basically showing right against the graph, that is basically the Sharpe ratio of the best sampled bit strings instead of the Cubo energy itself, right? I would expect if you're using Cubo, right, you would basically select the Sharpe ratio based on the energy that is getting minimized, right, and not the bit string itself. So why did you select the Sharpe ratio based on the bit strings?
Okay. So why did I select ratio on the sampling
Correct. Instead of the energy itself.
instead of the energy? So, we actually wanted to focus on the portfolio optimization, and we used the principal component analysis in addition to the QAO. So in addition to the QBO, so we didn't only use the QBO, we also used the principal component analysis.
And what exactly are you using that for, right? Like a bit confused, right? Like where does the PCA play a role here? We can't hear you. Hello.
Caleb, are you answering anything? We can't hear you.
Hello? Yeah, I'm back.
Yeah. Go on.
Okay. I don't think I have an idea about that.
Yeah, because see, what you are doing is you are using your PCA, right, to factor the model, right? And then you are building the cubo, right? And you're applying a cardinality, right? And then you are basically moving it into penny lane, correct? And solving it over there, right? So I'm
Yeah.
still not sure, right? Like after solving it, why are you still going for the bit strings? Maybe we lost them.
Move forward then.
Yeah, we can do that.
We can do it.
Thanks, Caleb. Yeah.
Can you stop sharing screen, Caleb? Yeah, next we'll go to the next team. Next team is team superposition. Are you guys ready? From team superposition, there is a Clyde Vela Crucis. Sure. Yeah, go on.
I'll be sharing my screen.
Please go on.
I think I might need permission.
Okay. You can't share your screen?
No, the option is not coming up. I'm getting a error message. Clyde, do you have screen share permission?
I'll just share screen.
Okay.
Oh my God.
Okay. Can you guys see it?
Yes, we can see your screen.
Okay. So there's our portfolio optimization using QAOA and also like VQA algorithms. First of all, portfolio problem cubo to quantum Hamiltonian, and then finally to ground state equals the optimal portfolio in which like an asset can be included or not. So why quantum? Finding the true optimal solution for like n assets can be like exponential number of checks. It can become shell heavy and approximations can get stuck at local minima. So quantum computers such as superposition and entanglement can have more efficient checks. And QAOA is promising because it alternates between the cost and the mixer operators, so it's high quality solutions. Overall summary of process includes our diagrams of quantum circuits on the left-hand side. So first we load in the data plus the QBO formulation, and then solving the QAOA. And then we do the backend, which we did Lightning.GPU, which is like a penny lane, which is like way faster than like Lightning.qubit. And then we do post-processing with like classical simulated annealing and like selecting the best solution for both quantum and classical. So filter for corporate bonds, which are but our main focus is the main fund because we want to extract the return from the bond characteristics, such as credit spread, duration, and current yield environment. And we also want to extract the risk matchers because that's one of the constraints in the problem. And yeah, we also did a cluster plot, which we did 500 assets, which includes 9 clusters of different types. So we loop to the n assets and then we like add points based on base market correlation, but we cap it at 0.825, so to make sure it balances out. So our step 3, we convert a Kuber problem, which consists of expected returns, risk mixtures, asset names, and current weights, as well as the matrix for sectors and credits. So we did this because we want our target basket size, which is 8 bonds or 8 qubits for optimization or number of bonds given. Portfolio has like 1,000 and yeah, and our risk is around 200. So that it doesn't like relate that much in terms of quantum and classical. So before we move on to step 4, we prepare a single bond bucket indexed by I and J, and we pull out the weight and target return. So we prepare the 2 structures shown below, which is the matrix and the linear terms. And then we also adjusted the risk return term by penalizing or rewarding tilting pairs in proportion of their joint exposure. And then we also apply negative bias linear reward for selecting each asset, so it helps us for target return and also add incentive proportional to the asset's expected return. So this is our over classical data, but no quantum computing yet. So as you can see on the right-hand side, you can see all the expected return around 5.3 to 6.8 of the all data. And then another example. So for this one, we'll build the VQA with the optimized QA circuit. We chose layers of adaptive layers of 2 to 6 because of the problem size. More than that, it's going to be like bad optimization. So, and this is just more information about our backend, and simulating 31 qubits is of course very computationally heavy. And then more examples. And then this is our like a main point. We did like 24 bonds or 24 qubits, and we did basket size of 8, which is still QA layers deep. As you can see, quantum beats classical by a huge amount based on the total violation. And their cost is negative 72K for quantum, and then roughly similar to classical because we haven't run on the real IBM backend. And yeah, more examples of quantum beats classical by like a huge amount. And yeah, more example, as you can see, Lightning GPU uses less memory usage than like the default baseline, which is my CPU. And yeah, I think that's about it for our presentation.
Great.
Thank you. I had a questions on your classical approach, right? I was reading your README, right? And you said like you use brute force benchmark, right, with simulated annealing, Bayesian hopping, right? That's not exactly brute force, right? It's more like, let's say, heuristic, correct? And so I'm still struggling to understand what exact classical solver did you use, right, for this particular problem, right, to sample it again? Because what I was seeing, right, in a lot of examples, right, the classical solution, right, that you were trying to build, right, it was not staying within the bounds, right? Like, for example, it was picking up more bonds than the target. If target was 6, it was picking up 8, 9 in some cases. And also, like in certain cases, right, classical had a more negative cost, but still, like you were saying, quantum still win. So can you explain me, like, what exactly you were trying to do classically?
I think the way we're trying to classical is just trying to compare like our quantum solution. Even though we didn't do it brute force, we just want to see like a quick checkup on like if it's going to be like better, which is in this case better, but we can also focus on that in the upcoming feature to better like compare benchmark on if we want to do brute force.
Yeah, because see, look at that classical solution itself. It selected 9 bonds while the target was 8, right? So it's not like you are comparing the right solution to the quantum solution, right? Because quantum did select 8, right, with the target of 8, but this one selected 9. It's where when the target was 8. So it's not like exact comparison where we can say, okay, one solution is better than the other.
Yeah, but we also did like more runs before that. But if, for example, if you do like 20 qubits, is the same, like select 8 bonds and then selected 8 bonds for both of them. And yet you can also see the difference.
If I can add on, I think the number of bonds that we selected was given a softer penalty than a few of the other things that we were looking at. We can definitely try to make sure that we're selecting the same number of bonds or enforcing a harsher penalty in the future, to kind of help with that one-by-one comparison.
Okay. And then I see you also spent a lot of time for the initial parameter optimization, right? Like you ran 50,000 shots, I see, right? Why was that? What was the reason of doing that instead of simply basically using expectation values, right? You could have used the state vector backend and done that. What was the reason for that? Like, did it improve anything? My question, like, let me you can more
I
targeted.
think
Like
we did like less.
spending a lot of time on.
We did
Yeah.
less shots, and we saw that it didn't have that much improvement. For example, 1,000 shots, but we just kept increasing it as we see fit, and we just found out that 50,000 improves our accuracy.
Okay. And then what constraints did you use in your Cubo? Like, did you use all the constraints, right? Or you stuck to a few constraints? Where is that list? If you can show.
We did. Yeah, there you go. We did basket size constraint, which we implemented soft constraint, and then we also did risk constraint and also the characteristics as our main metrics. Like, yeah,
So where exactly are you using the risk constraint? I didn't see them anywhere.
risk constraint in, let's see. In the, yeah, for if you can see like on one of the code in the risk, like exploring part 3 of step 1 to 5.py, for the risk the risk is also for the risk adjusted returns, like 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 double looping, and then we also did cross terms with real expected returns.
Yeah, but I did not find that risk characteristic, right, that you are calling out there in any of the code. So
Oh,
I couldn't basically backtrack it. Yeah.
it's like after the Cubo formulation around 357 lines. But yeah.
Okay. Okay, it's named slightly differently. Okay.
Mhm.
Okay. Yeah, I think those were the couple of questions I had. One more thing is basically see in your approach, right? What is happening essentially is that you are focusing on the cost, right? Which is basically your objective over here, right? And whenever you're trying to basically put in additional constraints to it, right? Are you scaling them or are you not scaling them, right? Because what I was seeing that like you are in some cases you are normalizing it, right? In some cases you are not. So that does impact the final solution quality that we get, right? And it can basically swing the solution quality in either direction. So did you do all those things right before jumping into it, or like you use the data as is?
Say that last line again.
Sorry?
Say that last line again. I couldn't hear that last part.
I'm talking about all the units that you used, right, in your constraints, plus the risk characteristics that you use, right? Did you scale them, right? Because a lot of those risk characteristics, right, they can swing. They can basically bias your output, right, and bias your solution. So did you use them as is, or you applied some level of data, what you call processing to those characteristics?
Yeah, we apply. Oh, before we load in the data, we just try to scale them to like make sure it fits like to our quantum algorithm?
Yeah, so I would recommend putting all that in README. It was not there, right? I
Okay.
did observe it's happening, but it was nowhere mentioned, right? So it will be good
Okay,
for people who are going through it to see where exactly it's happening.
Okay, we'll do that in the future.
Okay. All right. Yeah. Thank you.
Thank you. Thank you, team superposition. We'll move on to the next team, Anil portfolio. Mac, are you ready?
Yes, I'm ready.
Sure.
I'm going to share my screen.
Yes.
So is my audio good? Is my audio okay?
Yeah, it's okay. It's a lot of background, but it's okay, I think.
Okay, so a lot of background, or is this okay?
Yeah, now it's okay. Yeah, it's okay.
So noise or no noise?
Maybe I'll say a little bit noise.
Okay, I think let's go for that.
Sure.
So good day, everyone. So this is Hamak Yang, and I am a Neo Quantum. I'm introducing another method for portfolio optimization. I'm deeply grateful for having this opportunity to find my findings. So if you have participated in Romanium 2024 previous year, this is for you. So here's code I have so far. So have you seen my, so are you seeing my code? Are you seeing my code, or is there like any technical issues?
We see it.
Okay. So this is my code and my findings. Let's start this by running this presentation now. So good day, everyone. So this is going to be our agenda. So in this 5 minutes, we're going to introduce with a problem statement, the D-Wave solution, our results, and future scope. Our goal is to implement the simplified one-opto optimization model. So given securities categorized into risk buckets, let's say A, let's say AA, let's say AAA, we have to ensure the contribution of each of the characteristics like PTX, DTX, that they're close to the target. So K guardrail. So our loss model is a sum of squared residuals model. The problem matters because numerous trades happen every day at very high rates, and exact optimization becomes classically infeasible. Even approximate Gurobi optimization starts to fail due to local minima, which leads us to, because optimization is in matrix form, quantum annealing. So this is going to be our formulation of the solution. So let's C denote the set of securities. So each security has these variables like max min trades. Let L decide the number of risk buckets. In this case, we have capital goods, we have insurance, and we have transportation. Let J decide the number of characteristics, in which we will just simplify this to use just one, as according to the original model. So for each risk bucket characteristic, there's a guardrail and target value. Let's call this regular K. Then let bold K of L denote the subset of bounds in C, and then two global constraints. Our output value is the Y, which is the binary array indicating like whether like this bond is selected or not in like internal index order. This is going to be our equation. So C is 31, L is 3, J there's only PMV, and there's therefore like 3 bold Ks. We're going to optimize the constraints. So we have JT, JC, then JI, and then the R. Our D-Wave solution, after converting this to the QAOA matrix, we have this beautiful block symmetric matrix over there. We know like the red part, only the diagonal have the red because you can use expansion to convert this into D-Wave compatible format. Are going to show us our results. So this code over there is one of these optimal runs. we're able to successfully implement minimization of the objective function given the guardrail conditions, and it has demonstrated scalability at 65K runs and 31 bonds. It's able to run in only 3 minutes. This shows our D-Wave implementation is working in the next few slides. This is our bond limit. Over there, blue is the D-Wave energy. The orange is the QAOA objective function. The middle one is the cash flow, and the lower one is the bond selection in terms of canonical ordering, internal ordering, and the rest are the bonds that apply to each of the bold Ks. The shaded areas are the ones which are within the bounds. Now let's change the guardrails. So notice that as the guardrails expand, the energy goes down. When the guardrails becomes too narrow, D-Wave fails to find a feasible solution. So this shows our D-Wave solution is working. Let's compare this to the classical benchmark, which has been provided for us. So the reference uses a real Qiskit run with or without post-processing. The red line indicates the classical optimization, which let's say it's exact, so it's to be combinations. After post-processing, we're only able to like approximately get into the acceptable range. Can you hear me? I believe like there are some issues with my internet.
Yeah, we can hear you. Can you please conclude?
Sorry about that.
Yeah.
I apologize for this potential
No,
thing, but
no worries.
maybe like request an extension. So scalability and classical. Let's go back into the review. So this is where we change the bond limit. This is when you change guardrails. So notice that this is the code we have. Notice the red over there indicates that one bounds is too low. So once again, this is the bond limit. Notice if the n goes up, we're able to find a feasible solution, energy goes down. This is with 1,000 runs. Middle is the global variable for respecting the R boundary, and right are each of K boundaries, summed over those belonging to bold K of. Now we expand the light phase K guardrails and see that as feasible solutions come, or D-Wave is able to find satisfactory solutions and not get stuck. So K, then energy. Let's repeat the scalability and classical. So the reference run uses
Hey,
a real
Mac, I think you're almost 2.5 minutes. Yeah, just conclude your presentation. You're almost 3 minutes over time. Conclude your presentation.
Okay, so this is our larger data set with 283 bonds. So it's able to scale. It took 3 hours to run. We will conclude this with our future roadmap. So much time spent on coding also involves a lot of testing and code maintenance. So good code scalability and no code smells flowchart. But our limitations is, unfortunately, we are not able to get a real quantum annealer, which can support up to thousands of variables. We mostly discuss the smallest data set. And unfortunately, we will have to test our code with a full data set, but right now we're not able to rerun the code. We need to verify that my bounds match exactly those of the original for accurate benchmarking. Thank you very much. I hope like we do not have like this technical issue that I have potentially detected, but let's see if there's any questions.
Yeah, great presentation. Dr. Bimal, you have any questions?
Yes. So I would like to understand, right? What are the exact characteristics did you implement, right? It was not clear to me, right? And how did you define those buckets, like for your implementation? So can you show me that, right? Because I need to understand what is the meaning of amount, right, that you are talking about, and like what exactly does it mean, and how is it being calculated?
Okay, so the amount basically is based on the original 31 bond LP. This is our bond that we have, and I looked over the LP to determine and the guardrails there to translate this into the D-wave solution. So this is a D-wave bond over there. I
So
looked
when you
over
say, when you say guardrails, right? Which
Yes.
guardrails did you use, right? And were they like hard guardrails or versus the soft guardrails? Like, did you use them as penalty terms, or like how did you use them? Like that is also not clear here.
Okay, the guardrails are technically considered hard guardrails because I set them like the penalty term to a very high amount to ensure that anything that's infeasible would have a very high energy anyways.
Okay. All right. Then coming back to the first question, right? Like what is your amount? Because let's say you run this, right? The output is always a binary selection, right? You determine which particular bond is going to go into that basket. Then how do you reconcile, right? Like that error that you get, right, in that selection to the amount, right? Like that's why I was like confused. What exactly is the amount?
Okay, the amount, so is that the energy? Or
Yes, like the energy, right? Whatever you call the amount in your notebook.
Okay, so the amount, let's call this the energy is, there's actually two. The first one is the D wave, and the other one is the objective function. The objective function amount is just basically the sum of the squared difference between the PMV contributions of the bonds belonging to a bucket, let's say K of L. For example, all the transportation buckets, transportation bonds PMVs against the target value. So basically, like the target value there, it's expressed as both like middle target, which we really want, and is factored into objective function, and the guardrail target, which is basically the lowest and the highest, which we consider acceptable at all. And anything that goes beyond that is considered an unacceptable solution.
Okay. And which particular D-Wave simulator did you end up using? Like the result, right? The D-Wave result.csv file. So from where is it created? Which simulator did you use? Did you use the actual hardware or it use simulator to generate that output?
I'm able to use the path integral annealing sampler, but for the sake of time, we're not able to like compare this to the other type of samplers, nor we're able to use the leap.
Okay, so this is the only sampler that you used, right? The path integral one.
Yes, the path integral one is the only sampler that I have used.
Okay, all right. And another question is basically in the implementation, right, that you are doing over here. Slightly confused with the terminologies that you have used, right? So one of the things, right, when it comes to annealing, correct? It's basically how are you, let's say you have got this bit string, right? And then basically you are taking that particular problem, right, which is a cubo problem, right? So how do you measure the energy, right, of that particular problem over time, right, in annealing, right? Because you are using that particular simulator over here. Like how does that work, right? And how do you put the guardrail feasibility within that? Like, can you explain that slightly? See, I'm not too much what you call a hardware person, so I don't understand like how annealing works. But if you can explain that, right, like how does that happen when you run this?
This is because D-Wave supplies BQM model. The BQM model allows us to construct linear inequality constraint. So it actually supports this function over there. So if you go to part 3, you see like this over there. Sanity check. It's over there. So add a linear inequality constraint, and that leads to these Lagrange multipliers and slack variables over there. while the quadratic and linear terms are straightforward conversion of what has been calculated from in this matrix. So it's something that D-Wave supports itself.
Okay, got it. Okay, yeah, this is quite a unique approach. Thanks for sharing.
I really appreciate this idea. I'm going to pass on to the next. No, let's pass on to the next presenter. Although I do suspect that a technical glitch happened in the middle. Is there any technical glitch, or is it all good?
It's good. Almost it's very good. Yeah, good. No worries.
I apologize for that.
Yeah. So yeah, we'll go on to the next last team, but it's Shriram _ Shiplu. Hey, Shriram, are you ready?
Yeah.
Yeah, please share your screen. Go ahead.
Are you able to see the screen? Yeah.
Yes, we can see.
Good morning, everyone. My name is Sriram Javdekar, joined by my colleague Shipul Shakur. Today, I'll be discussing our work on scalable quantum enhanced portfolio optimization. Our team has developed a novel approach using Pauli correlation encoding to tackle one of the finance's most challenging problems. Core problem in portfolio optimization is finding the perfect mix of assets, like stocks and bonds, to maximize return and minimize risk. The challenge is immense. Add more assets, the number of possible portfolio grows exponentially, the phenomenon known as combinatorial explosion. This makes it impossible for even fastest classical computer to check every single combination. To solve this, we have formulated the problem as Kubo for quadratic unconstrained binary optimization model. Our objective is to find a binary vector y that minimizes the function you see on the screen, y transpose qy plus hyc plus h plus c. We have also incorporated real-world constraints such as those for risk embedded by adding them as penalty terms to objective functions. Our key innovation is using the method called Pauli correlation encoding, or PCE. The PCE maps classical variables to multi-qubit Pauli matrix correlation, which dramatically reduces the number of qubits needed for the problem. This is game changer for today's noisy, resource-limited quantum computers. PCE also helps mitigate barren plateaus, a major hurdle in training quantum algorithms. We extended this technique, which was previously used for max-cut problems, to Kubo with linear constraint for portfolio optimization. This provides a scalable and efficient solution for real financial challenges. Here is a brief look at how the encoding works. Each classical binary variable, yi, is encoded as a sign of expectation of unique multi-qubit Pauli string, also called correlator. For instance, the 5-qubit two-body X correlator consists of 5 qubits with 2 X states applied to 2 qubits. Similarly, for Y and Z correlators. Here, psi theta is parameterized quantum state. To construct it, we use hardware efficient SU2 ansatz. In practice, we replace the sharp sine function with a smoother hyperbolic tangent function with a scale alpha, which is set to 15 here, which is better suited for optimization. Using this method, we were able to encode the problem with 31 variables onto the 6 qubits, which can encode up to 45 binary variables. The table shows how we use two-body correlators to achieve this remarkable qubit efficiency. As you can see from the scaling, using n qubits allows us to solve a problem of size m of the whole n to the k, where k is the degree of correlation. We use a hybrid approach combining classical optimizer called Cobila with both ideal and noisy quantum simulations. We tested our algorithm's robustness by simulating it with noise from real quantum device, the IBM Discipline backend, using 2048 shots. This ensures that our results are realistic and achievable on current quantum hardware. This graph here shows the cost convergence using ideal simulator. You can see the cost function drops quickly and converges to near zero value, which is exactly what we expect from an ideal and noiseless simulation. Now this graph shows the result from our noisy simulation, which is more representative of real-world scenario. While the curve is a bit more erratic due to the introduced noise, the cost is still able to successfully converge, providing the robustness of our method even in less than ideal conditions. Our quantum solver successfully returned an optimal portfolio consisting of 21 assets, where when we compared our results to provided benchmark solution, our ideal simulation achieved the cost value of OD, which is identical to benchmark's optimal value. Even with noise, the solution from the IBM discipline backend gave us an optimal portfolio with cost value of 48.5. This demonstrates that our PCE VQE approach is effective and performs as well as the benchmark, even real quantum hardware simulated noise. This shows our method is not just theoretical, but can provide scalable, practical solution to real-world finance challenges today. Thank you.
Okay, thanks, Sriram. So I understand, if I understand your problem correctly, what you did is like you took the original problem, right, which was a linear problem, correct? Like with all the linear constraints, you converted that into an unconstrained cubo, right, using the penalties, correct? And after that, what you did is you converted that into a poly decomposition, right, the PCE. So my question on that is like, where exactly did you choose those penalty magnitudes, right, to do the conversion, right? And what was the offset, right, based on that? And then, like, also basically, if you can explain me, right, like what were the correlations or let's say the blocks or whatever you want to call them, right? Well, you need to collapse them, right, for implementing it on the PCE. Like, where does that happen? And like, what was the number, right? That.
Can you hear me?
Yeah, it's echoing, but we can hear you.
Okay, I'm Shiklu, so I'm his colleague. So if you can see, we actually use the exact loss functions you provided, right? The classical loss functions. And the basic idea is, how do you sample classic binary values? And that actually goes here. So if you see, each yi is basically coming from an expectation of an correlator. So the idea is we are not actually converting this into a Hamiltonian, but rather y is sampled from some expectation value. So it's a kind of a VQE kind of thing. So VQE here is used indirectly to sample these binary variables. And for this correlators, it consists of you can pick up like 2 body or 3 body. So what does that mean? 2 body means like you have 2 x's somewhere, 2 yy, 2 gz. So for example, here. So if you see, this is 31 bonds. So it grouped into three parts like 10, 10, and 11. And 10, first 10 are consist of 2 body X correlators. So, qubit 0 and qubit 1, they have X's, and rest of the base is I. Similarly, this X moves a little bit. So this correlator has to be different. But then the expectation value with respect to some NJAs, when you do these things, that gives you your Y. And that y is actually feeds into original function. So it's a nonlinear objective, but the y is sampled from VQE kind of approach.
Got it. So when you did this kind of encoding, right, for the PCE, like how did it impact the final circuit depth, right? Like, and the gate counts, did they increase? Did they decrease? Right? Like, did they stay the same? Like, what trade-off did you see?
So we actually didn't find time to explore, but I can actually see the NJAs. It's just a simple efficient SU2 NJAs with 2 repetitions. Since each of the correlators is 6 qubit, so we use the same NJAs for all. Only correlators are different. So these are used to make the parameterized answers. So you can tell like how many parameters it does actually have. Yeah.
Okay. Okay, all right. I think given the time, I think we can wrap it up. Thanks, Sriram and Shiplu.